Next, we have Zach Seibers, a research scientist at Georgia Tech, and he will be presenting on design and performance considerations of graphene-laminated thermoplastics for electrically conductive applications on the lunar surface in
Hi.
space.
Yeah, good afternoon, everybody. Thank you for having me, and I always enjoy this workshop, so I'm excited to talk here. So we can go ahead and go to the next slide. What I really want to discuss is some of our work relates to the use of various plastic materials, specifically thermoplastics, in this talk. And we're trying to think about things like we've talked about charging a lot and how that can interact with dust, how it can create problems in plasma fields. What we really want to be able to do is advance the use of or increase the use of different thermoplastic materials in space for a lot of reasons, but to do that we have to overcome some of the issues such as static charging, and that's where the electrically conductive component of this originally came from. Plastics have a lot of advantages, but one of the things that we really worry about, especially in this talk, is the lunar dust aspect, which we've talked about to a great degree. But just want to recall that the fibers and things that were used on the spacesuit deteriorated very rapidly, and that was due to abrasion. They didn't have any issues in those missions, but I think that this is going to be needs to be a big focus point as we think about long-term habitation on the lunar surface and extended operations. Next slide. So to kind of look into this a little bit and give you some background about our work, we've made a chemically modified version of graphene that we can spray onto various surfaces. We can use less than a milligram per centimeter squared to achieve coatings that are down in the 1 to 20 ohm per square range quite regularly. Despite these benefits, there's a big roughness issue with this surface. And I think that this is a problem, but one of my scientific queries is how much of a problem is this? And that is how much does the roughness and the porosity of the surface really affect the performance in a dusty environment? And so if we go to the next slide, what we've turned to in our research is a variety of applications where these laminate layers are promising, and we see a lot of good performance aspects. And so, for example, static charging, we're 10 to the 6, 10 to the 7 times better than we need to be on conductivity or sheet resistance, depending on which way you like to think about it. We are very interested in things like active lunar dust mitigation, thermal control. I think there's some real opportunities for coated plastics to provide really local heating in ISRU type scenarios, or as in more colder environments where cold thermal issues are a problem. It serves a little bit more purpose. I know usually on the lunar surface it goes the other way. But then of course we've got some other ideas here around neutron dosimetry, EMI shielding, and then of course structural monitoring, which has been mentioned a few times throughout these discussions. But at the end of the day, to do any of these things with a coated polymer or any kind of like softer material, even some metals would succumb to this issue. We need to know more about how they would respond to lunar dust. And so if we go to the next slide, the way I'm going to talk about this is just show some various substrates. These are all done on PEEK, which is a pretty robust thermoplastic. It's not your normal polyethylene bag by any means. If we look at this on the left, I've shown images as well as SEM micrographs in the middle, and then on the right is profilometry of 3 different samples that are represented by the rows. And what you're seeing here is differences in coverage, and then also the bottom depicts sort of a different processing arrangement that we can use to get better substrates that are more smooth and uniform. And in general, all the sheet resistance properties are all pretty good. But as you can see, we can get down to 0.2 milligrams per centimeter squared. So this is very, and we can spray coat these things. So this is something that we could apply to something like the spacecraft. I'll add that the roughness that you're seeing over here on the right, it progresses from being the texture of the graphene, and then eventually what we're seeing is the lines registering from the mold surface that we use to cast these samples or build these samples. And this is about a 1 centimeter by 1 centimeter area, or sorry, 1 millimeter by 1 millimeter area. Next slide. And so coming back to tie this in a little bit, where some of my questions come from as a material scientist trying to make contributions in this field, We know a lot of the things about lunar dust, specifically that it's got a very broad size distribution, and that there is some nanophase, there is representation in the nanoscale. And so one of the questions I have is, how confident are we in this? Because I think what it can do as a material scientist is help us establish design constraints. So at what point are these pores a problem? And again, it's one thing for a sample such as a piece of shielding on a spacecraft that doesn't really get actively pushed into the dust. That might be a different design constraint than something like a knee pad, which we know in Apollo was a big problem. And so if we want to, tune or engineer the surfaces of these various devices or materials, knowing more about this component would be good. And so I think that's the main size exclusion component that I really want to talk about. The electrostatic aspect is pretty much covered once you have a conductive material because you can dissipate the static charge, you can apply fields, and in more advanced cases, you can even apply an electrodynamic, dust shield. Next slide. So to look at this a little bit further, we took some various samples, we being my colleague Micah Scable, who's also in the Reveals research program. We've taken these samples, we put them in a special chamber that he's built for his work. I'm asking for a little bit more out of his environment than what he originally built it for. But the idea here is we can take dust, we can charge it with tribocharging or with an electron source or something like that. We can drop those charge grains down onto the surface, and we can do various things. We can apply a voltage to the surfaces. We can apply electric fields to the whole assembly. All that we are using JSC1A, and it's dried in vacuum and with heat and everything before it goes in. So these are pretty representative samples, kind of doing the best that we can do with this apparatus. So, but the thing I want to point out is that this is not a direct simulation of what you would see if such a material was used as a knee pad, for example, and really driven into the lunar surface. Next slide. Okay. On the left is the ADS prepared surface. You've already seen these images, the profilrometry scans rather, and then I've restated the numbers just so you can kind of see what we're dealing with. After we expose these to charged stimulant dust, we see dramatic changes. And I'll add that these surfaces are certainly on the rougher side. We wanted to try and tease out a result here, but there's a big difference in the roughness that we're seeing here. And as you can see by the profilometry of the starting condition. That being said, when we expose these things using the exact same exposure cycle, we see dramatic differences in how much dust is retained into the surface. And we don't see huge differences in the sheet resistance. I will admit that. However, I think the profilometry scans here are pretty telling as well as the images. You can see that the rougher surface generates a white, thick cake-like coating in areas. And whereas the smoother surface is much better at getting rid of that. I think that this is important to note because we obviously want to make these samples as smooth as possible. It makes sense from a physics and material science perspective that's going to be better at dealing with dust. However, as a design parameter, if you want to think about how to protect the suit or protect different materials, simple things like how this porosity and roughness, how do these types of factors play a role in this lunar dust environment is very important. And I'll just note the change in sheet resistance. Both of these are still plenty conductive for a variety of applications, but the point here is that there's a big change in the sheet resistance. And I think if we were to more aggressively expose these to dust, really drive them in or simulate that effect that you might see on a tool by an astronaut on the lunar surface, you would see much bigger changes in these values. And that brings me at the next slide.
Okay, 1 minute.
Great, thank you. So finally, what we're really trying to do is to take this idea, look at surface roughness with more. We've come a long way in our processing, and we've got examples here of this is what a spray coated sample looks like, and you can see the old sample here. This is what I showed. I took the sample that was exposed to the lunar dust environment was this little hole. And you can see that this surface is irregular. It does have some issues. If you were to put a tape test on this, you would actually, so just stick some tape on it and peel it off. You would see graphene come off around the corners. We've gotten virtually rid of all of those kinds of problems. And we have fairly perfectly uniform samples as much as you're going to get at this scale. This is about 2.5 inches by 5 or 6 inches in length.
Okay.
Um, and with
I
that,
think we're
yeah, I was going to say, with that, that's my last slide. I'm happy to take any questions.
okay. Okay, we're going to move on to, thank you, Dr. Seibers.